Okay, we now take a look at some example problems using Gauss's law, where we examine what happens when you have a conductor placed in the presence of an external electric field. We only do problems of this nature involving very symmetrical charge distributions or symmetrical shapes. So we're never going to have anything nearly as complicated as, say, calculating the electric fields near my electroscope. That particular demonstration has a configuration to the electroscope itself that's highly asymmetrical, and it would be next to impossible to make a calculation easily, at least by using Gauss's law in such a situation. So we keep the situations, in other words, with Gauss's law as easy as possible. So let's take a look at a couple of examples. Let's take a look at the easiest of the three examples that I have for you first. This is the following. Make sure, of course, that as always, you write the problem down into your notes. Okay, use Gauss's law to find the electric field everywhere due to a spherical conductor of radius capital R and charge capital Q. So the spherical conductor itself is charged, and the charge, capital Q, exists evenly distributed on the outside surface of the spherically conducting material. The reason why it's of an even distribution is because of the symmetry associated with the sphere. A nice example of this, by the way, would be the globe's surface, for example, of my Van de Graaff generator that you have seen in a couple of demonstrations. Okay, so we've got this spherical conductor like so. It has a radius capital R associated with it, and then evenly distributed over the surface itself is a total charge positive Q. Okay, now the electric field lines, as you've seen from a demonstration involving the Van de Graaff generator, are just simply radially outwards from the surface of the globe. So at the surface of the globe, of course, the electric field lines are perpendicular, like so, but then afterwards, due to the symmetry of the situation, of course, the electric field lines are radially outwards, that is, like so. Once again, by the way, in problems such as this, we automatically already assume that electrostatic equilibrium has been achieved. So what happens while electrostatic equilibrium is being achieved, we don't really care. We are only concerned with what happens afterwards. So in other words, this is already charged. Everything is evenly distributed. We have the electrostatic equilibrium condition achieved, and then we just go from there. Okay, so obviously we're going to conduct our calculations, that is, by constructing here spherical Gaussian surfaces. So let's go ahead, first of all, calculate what happens outside of the spherical conductor. So here's my Gaussian surface of radius small r. So here is now Gauss's law. Okay, so the left-hand side of the expression, as we've seen in other spherical problems, is E times 4 pi r squared. And then on the right-hand side, we have capital Q as the Q enclosed divided by epsilon naught. And then we just solve for E, and then you end up with the electric field associated with a point charge. Like so. Not all that surprising. But now let's go ahead and go inside the conductor. So when I go inside the conductor, right here is now going to be my spherical Gaussian surface. This right here, it has radius r. By the way, when we did this calculation, we were doing this for radius r bigger than capital R, but now let's go inside. All right, so when we go inside, immediately what we say is that the electric field is equal to 0. Once again, the electric field is equal to 0, remember, because electrostatic equilibrium has been achieved. There are no electrons moving within the spherical conductor at this point. The net force being exerted upon them is equal to 0. Therefore, the net electric field is equal to 0. On the actual AP exam itself, if you encounter a problem such as this, sometimes in multiple choice, they'll ask you to identify the graph associated with the electric field magnitude as a function of small r. It will look different, however, than the graph that we've seen previously for a spherical distribution of charge. That's not what we have here. Basically, what we have is just a piece of metal, a sphere, and all the charge is here at the surface of the sphere. So then therefore, if we graph this out, graph out the electric field as a function of small r, okay, right here is the surface of the sphere itself. And then therefore, for small r less than capital R, the electric field is equal to 0, like so. And then there's a point of discontinuity right here. The easiest way to think of that point of discontinuity is like taking a limit, for example, as you approach the surface of the sphere. And so then therefore, in terms of a limit, the electric field at the surface of the sphere would equal this quantity here. And then it drops off as a 1 over r squared relationship like so as we move out to greater and greater distances. Don't worry about the point of discontinuity itself here in terms of some sort of a calculation. In other words, just be aware that that point of discontinuity is there and it exists, and you understand then how to construct this graph, okay? All right, let's go on to the next problem. On the next example, we'll look at a specific case where an external electric field supplied by a point charge, in this case, polarizes a piece of metal. Okay, let me go ahead and do some erasing here. Okay, let me move my file. Okay, so the problem is as follows. Use Gauss's law to find the electric field everywhere due to a neutrally charged, spherically conducting shell surrounding a point charge, little q, at the center. The shell's inner and outer radii are capital R1 and R2 respectively. Find the charges that are induced on the inner and outer surfaces of the shell. In other words, the spherically conducting shell will become polarized. One moment, please. Okay, so let's go ahead and draw out the situation. It is as follows. Once again, this is a highly symmetric situation where we can easily use Gauss's law to make our calculation. Not so, however, in the situations that I described qualitatively in my last lecture. Okay, now let's go ahead and draw out the spherically conducting shell like so. Okay, right here is its inner radius, R1. Right here is its outer radius, R2. So this right here is empty space, and then this right here is a spherically conducting shell. Okay, and then right here at the center, this is a point charge. So a point charge is placed there somehow, and it's that point charge which then supplies the external electric field that polarizes the piece of metal. Once again, this right here is our piece of metal. So right here is a little q. Okay, now let's kind of start from the inside and work our way outwards, where we use Gauss's law to calculate the electric field in all regions of space. So let's start with small r less than capital R1. Of course, we're going to be drawing spherical Gaussian surfaces as we work. All right, so then therefore, immediately, the left-hand side of Gauss's law is, as it always is in these cases, E times 4 pi r squared. This then equals the q enclosed, which is the little q divided by epsilon naught. Once again, right here, of course, is our little q. We then solve for the electric field, and then we just get the electric field associated with the point charge. Like so, okay? Not all that surprising. Okay, and now we go right here inside of the piece of metal. That is between capital R1 and capital R2. Once again, we're only examining situations where electrostatic equilibrium has been achieved. So then therefore, immediately, what can we say about the electric field inside the conductor? It's equal to 0. However, if the electric field is equal to 0, what must the q enclosed be? It must also be equal to 0. So then therefore, a charge is induced on the inside surface of the spherically conducting shell. That charge that's induced on the surface has to cancel out the little q. Let me draw our Gaussian surface like so. So if our Gaussian surface in this calculation is like this, and because the electric field inside is equal to 0, this then means that the q enclosed has to be equal to 0. Therefore, we have to have a charge that's induced on the inside surface of this spherically conducting shell to cancel out this positive q. In other words, there's a negative q that's induced. That negative q is evenly distributed over the inside surface here of this spherically conducting shell. We can describe it, if we wanted to, in terms of a charge distribution, a charge density in this case, which would be charge per area. So on the inner surface, the charge per area that's induced is equal to this minus q divided by the surface area of the inside surface, 4 pi r1 squared. Okay, now let's move outside of the sphere. So when we move outside of the sphere, let's go ahead and draw another Gaussian surface like so in order to illustrate. And then let me draw another radius. Here we go. Like so. Right here is the radius r of that Gaussian surface. So now we have r greater than r2. Okay, so E times 4 pi r squared is equal to Q enclosed. Let me write that first, divided by epsilon naught. Okay, well, what is the Q enclosed? Well, the Q enclosed is just this point charge Q. But now you may be saying to yourself, well, wait a second, what about this minus Q that's evenly distributed here? What this then means is that you have to have a positive charge that is induced on the outside surface of the sphere. In other words, we have to have a positive Q that's evenly distributed on the outside surface here. So this positive Q plus this negative Q plus this positive Q gives us then the charge enclosed, which is just the positive Q. And then we solve for E, and when we do, we end up with, once again, just the electric field of the point charge. So in other words, this piece of metal here in blue has now become polarized. This is the negative side of that piece of metal. This right here is the positive side of that piece of metal. The inside surface has a total charge of minus Q. The outside surface has a total charge of plus Q, such that the total is equal to 0. It does say in the problem that the spherically conducting shell is neutrally charged, so the total amount of charge associated with it has to be 0 the whole time, and it is. Okay, now even though this charge here on the inside surface and this charge here on the outside surface is the same, they have different charge densities. This right here is the inside surface. For the outside surface, the charge density sigma would be positive Q over the surface area of that sphere, 4 pi r2 squared. So notice that these charge densities are different because of the different radii, even though the charge Q is the same in magnitude, just one being negative and one being positive. Once again, this is basically the exact same thing as my electroscope demonstration. It's the exact same thing that I was describing in my qualitative lecture that preceded this one. It's just that in this highly symmetric situation, we could easily use Gauss's law to calculate what is happening. You may be asked to identify a simple diagram that shows the net electric field in this situation once the piece of metal has become polarized. That diagram looks like this. Okay, so here in blue, let me once again go ahead and draw our spherically conducting shell. Okay, here's my plus Q from earlier. And then inside the cavity here, we just have the electric field associated with a point charge. Okay, this is once again the net electric field. The net electric field here, you'll notice, is perpendicular to the surfaces here, 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 and so on. But then inside the spherical conductor, the net electric field is equal to 0. But then outside of the conductor, the field lines then just continue on their way, if you will, like so. You have the electric field associated with the point charge. That is like this. So electric field due to a point charge, no electric field, and then out here, electric field due to a point charge. With respect to other types of problems involving Gauss's law with conductors, there are a few variations that you may see. Just for variety purposes, let me go ahead and finish this lecture with an example that shows some of the variations that you might encounter. Okay, let me move my file. And let me do some erasing. Okay, every now and then you'll encounter problems where the shells are thin. When it says thin, this then means that you can neglect the thickness of that shell. So just for variety's sake, here's an example like that. So two concentric, thin, spherically conducting shells have charge distributions sigma 1 and sigma 2 respectively. The radii are R1 and R2 respectively. Find the electric field everywhere. So here's what we have. We have, first of all, a really thin piece of metal, like so, a spherically conducting shell with a radius, capital R1, and a charge density, sigma 1. And then we have right here, surrounding it, another piece of metal, like so. So this is a piece of metal, this is a piece of metal, this is empty space, and this is empty space in the problem. Okay, and then right here is the radius, R2. Okay, the outer surface right here, it has a charge density sigma 2. Okay, it then says find the electric field everywhere. Once again, we just kind of work from the inside outwards. Let's go ahead and see what happens here inside the cavity. So little r for our spherical Gaussian surface is less than r1. Immediately the electric field is equal to 0. Why? Because there's no Q enclosed. So this is completely empty space, there's no charge there, so then therefore the electric field is equal to 0. Okay, and now we go to, let me go ahead and draw it here. Like so, where right here is now the radius of our Gaussian surface. Is there a Q enclosed? Yes, the Q enclosed has to do with this charge that's distributed here on this surface, and it has a charge density, sigma 1. Now, because the problem is stated in terms of charge densities and not charges, we have to write the answer in terms of charge densities. So let's go ahead and work through it. Okay, so now we're in this in-between region, that is between R1 and R2. So now we're going to have E times 4 pi r squared, like so. And then on the right-hand side, we need the Q enclosed. We'll do that in terms of sigma. Sigma, remember, is charge per area. So if you take charge per area and multiply it by area, that then gives you charge. So then therefore, charge per area multiplied by area, like so, the surface area of this really thin conducting shell. And then divided, of course, by epsilon naught. Okay, notice the 4 pi's cancel out, like so, and then you just solve for E. So in doing so, you get sigma 1 r1 squared divided by epsilon naught r squared, like so. So this is just a point charge electric field when you're outside here in this in-between region. Okay, and then we'll move outside of the whole thing. So here's our spherical Gaussian surface. So if in this case, radius small r, so now we have small r greater than r2. Okay, so E times 4 pi r squared, and then we have to get the Q enclosed. In this case, the Q enclosed is not just going to be the sigma 1, but we also have to add to it a sigma 2. Once again, you do charge per area multiplied by area in order to obtain the charge. So then therefore, on the right-hand side of the expression, I'm going to have sigma 1 times 4 pi r1 squared plus then sigma 2 times 4 pi r2 squared, and then all divided by epsilon naught. I know this is a little messy. Let me go ahead and move to the lower board. Okay, so let me just rewrite it. So E times 4 pi r squared equals then sigma 1 times 4 pi r1 squared plus sigma 2 times 4 pi r2 squared, and then all over epsilon naught. Okay, the 4 pi's all cancel out, and then we just solve. So the electric field is sigma 1 r1 squared plus sigma 2 r2 squared, and then all divided by r squared epsilon naught. Okay, there are a few other variations that are similar to this, but hopefully, as you can see, the basic process of setting up and solving these problems for these highly symmetric situations, usually involving spherical conductors, is pretty straightforward. That concludes chapter 22.